So thank you guys for coming to our special summer seminar. We'll have two speakers today. These are two of our CAPS graduate fellows from this academic year. We have Amanda, who is a student in the astronomy department with Gotham, and Maggie, who is also a student in the astronomy department working with Decker. So they'll each be telling us a bit about the work they've been doing this year.
Hi, everybody. Thanks for your patience. I'm Amanda Wasserman. I'm just finishing my fourth year as a PhD student in the astronomy department, working with Gautam Narayan, as Cynthia said. And today I'm going to talk to you all about the Vera Rubin Observatory LSST recommendation for system for spectroscopic follow-up, or RESSPECT. So a really quick background about LSST. I think most people know at this point, but LSST is going to be a wide field survey. It's going to observe 1,800 square degrees of the southern sky every few nights at the Rubin Observatory for 10 years. We're going to have, by the end of it, about 60 petabytes of data, first light in 2025, which is actually going to be something like this month or next month, so really, really soon. And it's going to enable a ton of different science cases, so things like studying variable stars, strong lensing, active AGN, and what I'm most interested in, transients and dark energy. So simply because of the pure quantity of data we're going to be observing, LSST is going to be a transient discovery machine. We're going to increase the discovery rates of supernovae by about 2 orders of magnitude, going from, say, about 10 supernova we're finding a night to over 1,000. Some things about LSST, just because we're going to be seeing so many different objects, we're going to find supernovae early. And if we can follow up on them early enough, we'll learn a lot about their progenitor systems. We can do things like better type 1a modeling if we can learn about those progenitor systems. And from that, we can find things like more accurate cosmology. Also, simply from the sheer quantity of data, we're going to find rare transients, things that we've only found, 1 or 2 of in the past, or that we've only theorized. We're going to see, maybe not in abundance, but handfuls of these objects instead of maybe one. Things like kilonova, calcium-rich transients, parent stability supernova, all these kind of things we can expect to find in LSST as long as we can extract them from that needle in a haystack of data. But despite all this really, really interesting science that LSST is going to discover, we're only going to be able to spectroscopically follow up on less than 1% of this, down from about 8% of what we're seeing now. And spectroscopy is the main way we learn about all the different really interesting science within these objects. So that's how we learn about their environments, what they're exploding into, what elements they're made up of, their progenitor systems. And it's also the way we find out specifically with more certainty what type of object it is. So say type 1a supernova versus like a type 1b supernova, which is really important when we're trying to analyze for cosmology. We want to make sure we have the purest sample possible of type 1a supernova when we do a cosmology sample. So some things have become very, very clear from this is that, one, we're going to need a way to find these scientifically interesting objects, these needles in the haystack. And 2, we need a way to coordinate the spectroscopic follow-up, especially prioritizing that early time spectroscopy where we'll get the bulk of our science out of it. Luckily, the Dark Energy Science Collaboration Desk thought about this in 2019 and worked with the Cosmos Statistics Initiative. And with Emily Ishida, they led the recommendation system for spectroscopic follow-up, or RESSPECT, which is an algorithm that will recommend on order 10 supernovae per night that we want to follow up on and get spectroscopy. If a recommendation system sounds familiar, that's probably because it does. We see these in our everyday lives with things like Netflix and Spotify. These different places analyze things that we watch, that we listen to, takes into account what we like, what we didn't like, and based on that can recommend what we want to watch or listen to next. And similarly, RESSPECT goes in and says, okay, what do we know about what we've seen before? What have we learned? And based on that, what will be most useful for us to follow up and learn more about next? What we are looking into right now specifically is with type 1a cosmology. This is the metric we're analyzing. So what we have here is that we'll get alerts from LSST. Those will go through the brokers and into our target observation manager. And all those alerts will flow into RESSPECT. RESSPECT will analyze these light curves and classify them as either type 1a or not type 1a supernovae. And maybe unintuitively, it will actually go and recommend following up the things it is least certain of. And so get spectroscopic follow-up, get a more accurate idea of what class it is, and then add that kind of weird, uncertain object back into the training set with an accurate label. And the next time that the algorithm will see something funky in a similar manner, it will have a better job classifying that object. This is something that's called active learning. And yes, basically just iteratively adding the objects that will maximize new information into the training set. So at the end of the 10 years, we'll have a really good training set to classify photometrically all the objects that we see with LSST and use those photometrically classified 1As in a cosmology sample. So just a little bit deeper dive into RESSPECT. We can start with a baseline set with as few as 10 objects. Those objects become our training set. We train a classifier and then take in a pool set, or say those 1,000 supernova that we're seeing each night. We classify that pool set and give them a probability of whether they're a type 1A or not. We take into account our active learning strategy. So that's when we pull out those things that are really on the 50% line, the things we're not certain if they're 1A or not. We also take into account telescope resources and the object properties. So we're not going to recommend objects that are going to take, 8 hours of observing spectroscopically. That's just not feasible. So we make sure to take into account those properties, nothing too dim, nothing that will take too long, into our follow-up strategy. From this, we'll get a candidate list that will then go on to a human to kind of parse through and make those follow-up decisions. We will then query the objects, send them for spectroscopic follow-up. And once we get that follow-up, we can append the label, the true label, to the light curve and add it back into the training set, increasing that now training set from 10 to say 20. And as those years go by, getting 3,000 objects in the training set each year. So obviously LSST isn't online just yet. So what are we using in the meantime? What is the flow of RESSPECT looking like right now? We're using ELAsTiCC. This is a simulated data set containing about 5 million transient events. Within it are about 25 different classes of objects between supernova, AGN, all sorts of different things. They contain an LSST-like alert structure, which means in the coming months when we start getting alerts from LSST, we'll be able to start running our algorithm on it as soon as possible. And then once we have the light curves from ELAsTiCC, we are able to do feature extraction from these light curves. So right now we're using a package called Light Curve by Kostya Malenchev, one of Gautam's previous postdocs, which finds things like reduced chi-square, does a linear fit, takes the time duration of the object, analyzes all sorts of things like this, and pulls out features that we then feed into RESSPECT, and RESSPECT does its classification. So once it pulls out those things that it's most uncertain that ride that 50% line, we can do spectra simulation. We're working with a team at Foremost. They are kind of like DESI. They're a multi-fiber object observatory that will come online in the next year or two. And they have a program called TIDES, which will be specifically following up on supernovae. So we are working with them to create the first realistic simulation of LSST. What we do is we pull those, say, 10 objects that RESSPECT finds to be most worthy of follow-up. We can simulate a SED through SNe Ia, this supernova modeling pipeline. We get that SED in orange up on the right, but that's a bit too perfect for what we want, right? That's not what real spectra is going to look like when we follow up in real life. So we worked with Foremost to use their exposure time calculator to get realistic spectra. You could see that blue line there. And that's basically going to be what our follow-up is going to look like each night. So once we have that spectra, we can feed it into DASH, the Deep Automated Supernova and Host Classifier. So DASH will classify these algorithms, these spectra, it'll find a best match class, and will also estimate a redshift. But what I think is also really interesting is that instead of estimating a redshift, you can put in what redshift you think it is, some prior on the redshift. Maybe you have photo Z's, something like that, and you can get a better match of class based on some priors that you know about redshift. So how are we communicating between RESSPECT and all these other telescopes? So I've been working with Rob Knopp on FastDB, the FAST database. And basically from the recommendation side, from the RESSPECT side, we can ask to find hot transients. So basically query all supernova that have a new point in their light curve from the previous night. Once we have those, we can classify them and then decide what we want to follow up on, and then respond to the FAST-DB and say, hey, I want a spectrum for these objects. And then once the information is returned, once the spectra is retrieved and added to the database, RESSPECT can then go in and ask for information about the spectrum to be added back into the training set. Then from the follow-up side, from the spectroscopic follow-up side, different telescopes can query what spectra are wanted. So, hey, what did RESSPECT say that it wanted in the previous nights? Great, awesome, let's go look at that. They can declare an intent to take a spectrum, which I think is really important because we don't want two observatories to take spectra of the same object in the same night. Our resources are really limited, and we want to make sure that, yeah, we're using our time as well as possible. And then once those objects are followed up on, they can report the spectrum information back into the database. So I think it's important to note that multiple spectroscopic recommendation systems can recommend. I've been talking about this kind of 1A classifier, but you could imagine something like an anomaly detection algorithm that would also be recommending, and all these sorts of different types of recommenders all pushing the recommendations to FAST-DB for these telescopes to follow up on. And then anyone can access these recommendations. Like I said, we want to be maximizing our follow-up resources. So, we can say anyone can come access these. We just request that you submit a classification and label once you have observed that object. So great, let's dig into results. So I have run the RESSPECT on 1 year of the ELASTiC data. This is using a random forest classifier and adding 10 objects each day to the training set. We're currently not using that SED simulator. Right now, we're just using the true label of the object. And we can see the difference between uncertainty sampling, so that 50% line of don't know if it's a 1A or not. And we're also looking at random sampling. So basically saying every day, let me just pick 10 random supernova and stick them into our training set. And we can see that we are improving each night as expected. So as you put more information into the training set, we're getting better accuracy, better efficiency, everything like that. The thing I really want to focus on also is the figure of merit. So this kind of rewards on the efficiency on acquiring all the type 1 supernova that are out there, and punishes for wrongly classified non-1As, so false positive 1As. We want a really pure sample. So the W in that equation down there is 3. So by a factor of 3, we are punishing for false positive 1As. And yeah, looking really good. We can compare these to Emily Yoshida's results from 2019 in the initial RESSPECT paper, and we can say we're matching up quite well, especially in that figure of merit, really matching up where our uncertainty sampling is quite surpassing our passive learning. A couple drawbacks that we're seeing right now, though. So this is the year 1 confusion matrix on the left. So getting all those light curves from year 1 and passing them through our random forest classifier, and then on year 2 and 3 in the right. And we can see that in year 1, we're doing a much better job classifying than year 2 and 3. And we believe this is because in year 1, we have a rolling cadence, and in year 2 and 3, it's the full sky. So on the left, we're seeing much denser light curves, and on the right, much sparser. All of our training data is from year 1. So we think because of that, it's more representative of year 1, and therefore does a better job classifying. A couple of ways we're hoping to mitigate this is, instead of using those light curve features, is to move to using a variational autoencoder. This is something that actually Gautam's postdoc Jack O'Brien is working with some folks at Northwestern, Jiazhong Wu. They're working on a VAE, so we're hoping to use the encodings from that VAE as inputs into our random forest classifier, and yeah, hoping that they will be more representative even with sparser light curves. Some other improvements we think we can make before LSST comes online is improving DASH. DASH is great, but it was made in 2019. There's been a lot of improvements since then. So we're working with Yuqing Yu at Northwestern as well. So she's taking a transformer-based approach to classifying spectra. This means that we have to do minimal pre-processing. We can have any range of wavelength input into the algorithm. And we're training and testing on WISE-REP, which is basically a database of all the spectra that we have in the field right now. And so you can see on the bottom left, we're far surpassing what Dash was doing in the past with just, we've been working on this for about 2 months. So even in that 2 months, we're really improving on what Dash was doing before, and we're hoping to keep improving on this. You can see a really diagonal matrix right there. So everything's looking like this is coming along swell, and we'll have this ready in the next few months as LSST comes online. Another improvement we're hoping to make is to move from this random forest classifier model to something a little more sophisticated. This is the Oracle classifier by Ved Shah, one of Gotham's previous undergrads. This uses a hierarchical classification approach. So basically, it classifies things at a higher tier before moving on to the lower tier. So it starts with saying, is this a transient or is this something that's periodic? And then it looks at like leaf nodes below that and says, well, is it a supernova or is it something that's not a supernova? And then even below that, what kind of supernova is it? And so this lets us kind of look at higher up groupings, and you can see, let's see, up in this corner, you can see even within the confusion matrix here, there's kind of the square within the supernova. So even though it's confusing some things as other types of supernova, you can see it does a really good job of saying, yes, it is a supernova. This is also really important for photometric follow-up. If we know something is a supernova, we can follow up with something like DECAM, maybe ZTF will follow up on it, and get denser light curves to do a better job of classifying it photometrically in the future. Also, we can see that Oracle does a really nice job classifying with only 10% of the light curve visible. This means that we're going to do much easier early time follow-up. So once we can classify something with 10% of the light curve, we'll be able to follow up on things as early as possible, maximizing the science we can get from each object. And this is super preliminary, but I'm working with Ian Mitra, one of the CAPS postdocs, to follow up on our final cosmology analysis. So this on the left is a completely pure sample of type 1a supernova, and on the right is a set of contamination from core collapse, I think about like 10%. And we can see that the pure sample of type 1a has much stronger constraints than the contaminated sample. So this is not yet with our RESSPECT probabilities of what types of objects are, but this is just an idea of what it might look like once we finish this cosmology results. So this is great. We really like this recommendation system and saying, how we want to get from light curves to spectroscopy. Our question then became, who else could utilize this? So we worked with the LSST link incubators. I spent basically the entire fall doing this. And we had some goals, which was to make the recommendation system accessible to all, pave the way for a modular approach, basically say who else's science cases could really utilize this, and then document it and make it really easy for folks to come in with their own science case, plug it into RESSPECT, and use it for what they want to do. The first module that we kind of were working with and got into this modular approach was this anomaly detection, light curve anomaly identification and similarity search done by Patrick Aleo. This is an algorithm that will analyze light curves using random forest and a similarity search to find those anomaly events, the things that are least like other events. And this will tag exotic transients up to weeks before a human would. So this is just an example of an object that we actually chose to follow up on. This is a type 2b supernova, one of the rarer types, and we chose to follow up on it, but the algorithm would have recommended 10 days earlier to follow up on it. And so again, that's just where we're going to get the majority of our science results. So the earlier we can find it, the better. So an algorithm like this is super ideal. And LACE is actually sending real-time alerts right now into the Young Supernova Experiment Slack. It'll send, however many things it finds that day that it believes are anomalies. And then a human can come in, look at those Slack alerts, and decide what they want to follow up on individually. So we worked on incorporating this into RESSPECT, and now we are basically able to include pluggable science cases, especially with the help from Haley Perkins and Drew Oldag. You can now come in and create your own feature extraction method, create your own classifier, and as long as you have them deployed as packages, you can really easily plug them into RESSPECT. You just have to basically import them into the same environment, and it's easy as a few lines, and there you go. You can plug your own science case into RESSPECT. Something that we didn't quite get to in this project that I'm really hoping to one day get to, though, is creating a web interface, something like a scroll down menu of picking what science case you're interested in, say anomaly detection. RESSPECT will come recommend all the objects, and you'll able to look at postage stamps, all that information. You can click on one, perhaps see the light curve, analyze for yourself. And then within this web interface, we'd really like to be able to just select an object, add it to your follow-up queue, and right in the interface, send it, say, to the target observation manager, and have your object scheduled for follow-up right in this web page. Just a couple examples of some modules we would love to expand to, something like kilonova, lensing, tidal disruption events, changing look AGN, something that Maggie might be interested in, might talk to us about next. And truly anything can be incorporated. Whatever you're interested in, we'd love to talk to you and be able to add your specific science case into our algorithm. So quick summary, we're going to have a much needed recommendation system ready for LSST's first light, and we've had successful tests on this end-to-end system. And just some future plans that we want to do is get out this final cosmology contours, and once we do that, we'll submit the paper showing the improvements that RESSPECT will make on the LSST cosmology sample. We want to update that classifier from something like the random forest classifier to Oracle. We'd like to do this updated, more representative features. And finally, yes, do adding more modules, making this accessible for more folks within LSST and the wider community. So thank you, and I'll take any questions.
Thanks for the great talk. I'm curious, is light curve the only input for the system? Do you consider also include images and take like the morphology into account?
Right now, the only input is light curves, but I mean, we're not even adding the light curves as our input, right? We're doing this feature extraction. So you can imagine having your own feature extraction, which also includes, something like gravitational wave alerts, something like neutrinos, whatever you're interested in, you could probably create, a feature extractor method that would incorporate that into the features.
Hello, everyone. My name is Maggie Verrico. I work with Decker French, and I study changing look AGN. We'll talk about what those are. And I'm really excited to get the opportunity today to present the results of my CAPS project. So thanks to CAPS for funding this work. We are looking at changing look AGN in ZTF to try to catch their transitions and understand their origins. So just a quick outline of the talk. First, we'll talk about what changing look AGN actually are. I'll talk a bit about the methods I've used for this analysis, some preliminary results, and finally some preliminary conclusions and sort of the last steps to wrap up this project. So let's start with changing look AGN. All right, so AGN can be broadly categorized into two types. You have type 1 AGN, which are sort of classified based on their broad line emissions. So you can see here broad H alpha, broad H beta, and type 2 AGN, which are lacking that broad line emission. And an easy way to sort of remember this is that type 1 is bright, it's blue, so you can see that blue continuum over there on the left, and it has broad line emission. Type 1, not quite as easy to remember, it's dim, red, no broad lines, so just the opposite of a type 1. And the way that we normally explain this is something called the unified model of the AGN. So the idea here is that all AGN are supermassive black hole accretion systems. So you have a supermassive black hole at the center, you have an accretion disk around it, which is emitting this sort of UV continuum. You have these gas clouds around that accretion disk, which are virialized, they're moving really quickly. And all of this is enshrouded in the dusty torus. So this is a dusty sort of donut-shaped object that surrounds the accretion disk. And so if you are lucky enough to be oriented such that you can see the supermassive black hole and its accretion disk, you're able to see broad lines emitted by that gas that's moving really rapidly in the center of the system. You're able to see that bluer continuum from the disk itself. But if you're unlucky enough to be stuck trying to peer through the edge of that dusty torus donut, you are unable to see those broad lines, and so you see a type 2 AGN. And this would work super duper well if it weren't for changing look AGN. So changing look AGN are switching between those two types. They are gaining or losing broadline emission on timescales less than a decade. This is an example object here. You can see that when an SDSS spectrum was taken in 2000, it had broad lines, so broad H alpha, broad H beta, which had completely disappeared by 2010 when SDSS went back to look at it again. And unluckily for us, most of these objects have been found in SDSS. So we have a spectrum from 2000 or the early 2000s, we have a spectrum from the 2010s, and we have no other information about what has changed. We just know that these broad lines have disappeared. Rates for how often this occurs vary depending on how you decide to select, but generally there's agreement that these are occurring in something less than 1% of AGN. And these objects, which have been classified in the optical, are thought to be changing state AGN. So specifically, this is a change in the accretion rate rather than some sort of change in obscuring material moving in front and blocking your view of the broadline region. And so people are trying to explain this, and they've come up with a few sort of broad categories of theory. The first category is that this is some sort of disk perturbation. So the most common here is a tidal disruption event, or a star which is torn apart by a black hole and deposited onto the AGN accretion disk in this case, causing a spike in the accretion rate, which changes the appearance of the AGN. You could also have some sort of fueling transition, so a change in the availability of molecular gas to that accretion disk, causing a change in the broadline appearance. And you could also have some sort of instability in the accretion disk itself, causing a localized change in the accretion rate and causing a change in the appearance of the AGN. So here I'm showing, for example, the propagation of a cooling front. And so these sort of three broad categories of theory are our best guesses at what's going on here. But as I showed just a second ago, we have, a spectrum before and a spectrum after, and nothing in between. And so we have to be a little bit creative about how we figure out what actually happened here to cause this change. So before I received the CAPS fellowship, I worked on using changing look AGN host galaxies as a way of figuring out what was going on, in particular testing those disk perturbation and fuel transition theories for changing look AGN. And so this was very recently accepted and is out on the archive. I'm not going to go into it today, but I'm happy to talk about it after. Essentially, I find that there's not great evidence from the host galaxy's perspective to support changing look AGN being driven by a fueling transition or by a tidal disruption event. So in the case of a fueling transition, you might expect some sort of signature in the star formation history, whereas fuel runs out for the AGN, it also runs out for star formation. So we don't see anything like that. And further, we don't see evidence of significant starbursts in the star formation histories of changing look AGN, which would be associated with tidal disruption events. And so really, when we go back to this sort of set of theories, this is starting to point us in the direction of something maybe a little bit more like a disk instability. And now all of a sudden, our host galaxy tools, as much as I would like to use them, are not quite as useful to understand what's going on. We really need to get a better sense of the physical changes through the transition. And for that, we're going to want to think about things in the time domain. And so I'm taking a little lesson here from another group member, Nick Earl, who put out a paper earlier this year on a tidal disruption event, AT 2020 NOV. And the way that he was able to understand what was physically changing in this system was by modeling both its light curve and this high cadence spectroscopy. So because we have these systems like the ones that Amanda mentioned, that sort of let us know when a transient event is occurring, we're able to go get follow-up data, follow-up spectra, and sort of trace the physical transition through time to understand what we are seeing. And so you can imagine that it would be very hard to learn things about tidal disruption events if you had a spectrum before and maybe a spectrum at peak and nothing else. And that's sort of the state that we're in with changing look AGN. And so what we need is a way to alert us to something like a changing look AGN transition, and to use the light curve and hopefully at some point high cadence spectroscopy to understand the physical changes that are occurring that cause this disappearance or appearance of the broadline region. And so that's what I'm thinking about when it comes to this CAPS project. How can we get something like this for a broad sample of changing look AGN? And so let's talk about it. How can we actually solve this problem? Well, as Amanda messaged, mentioned, oh my goodness, LSST is now working. We've all been to hopefully some first light events. And so very soon we're going to have all of these free light curves of basically every object in the southern sky. And so this is a really great opportunity as a time domain scientist to catch some changing look AGN in the transition, follow them up, figure out what's going on. So when I proposed for this project, I used the on or broad line state and off or narrow line state spectra, put them into Rubin Sim, which allowed me to make mock photometry for those spectra, what Rubin would actually see, and make some predictions about the color changes and magnitude changes that we expect for the changing look AGN transition. And so we're able to take these predictions and use an existing time domain survey, the Zwicky Transient Facility survey, to try to find these kinds of transitions in changing look AGN light curves. And in particular, what we're interested in is, can we find these objects in LSST, trigger follow-up, and understand what's going on? So here's an example ZTF light curve for a changing look AGN. And as with many of the changing look AGN, our archival spectrum is before ZTF ever turned on. So there is some time where we might miss some sort of changing look AGN transition. But you'll notice the follow-up spectrum, the more recent one where the AGN was off, occurred when we actually do have some ZTF coverage. So we can hope that we're going to get lucky and catch some of these changing look AGN transitions as they occur. And we're looking for something like this. So AGN are always varying, but this is a changing look quasar in particular, which was found in a recent paper, which was repeating. So once long ago, it had broad line spectra. It dimmed, it then had narrow line spectra, and then it re-brightened over the course of a little over a year. And so this was caught and followed up, and this sort of sigmoid or step function kind of light curve, this is really our golden case. TDEs don't look like this, supernovae don't look like this. This is something that changing look AGN do that other things don't do. And so what we want to find are light curves that look like this one. So I'm using a piece of software called Piecewise Linear Fit to fit a bunch of light curves and look for this kind of step function behavior. So this is actually the same light curve as this object. I have it in my sample. So first of all, we want to make sure that we can recover something like this. And to start this, I visually identified a couple of objects that looked like really strong candidates for the changing look transition. So I had this object and one other, and then 4 other objects that looked like maybe they were undergoing a similar type of light curve as these two. And so we're going to fit all of these objects, all of my changing look AGN, which is about 180, with piecewise linear fit. And we are going to see if there's anything that jumps out in these changing look transitions that is distinct from normal AGN variability. And so to start off with, I compared to a set of simulated light curves, simulated damped random walk light curves, to just try to see what would piecewise linear fit pick out of normal AGN variability so that we can sort of remove that from our sample. We don't just want to be picking up on regular AGN variability, we want these changing look AGN transitions. So I simulated 60 damped random walk AGN light curves and fit those with piecewise linear fit and compared what I got out of that from my piecewise linear fit fits to the changing look AGN light curves. And specifically to the G band here. And so what we see is that in terms of the amount of time that it takes for a transition to occur, AGN variability occurs on all timescales, and piecewise linear fit picks out AGN variability on all timescales. So we don't see anything distinct in the sort of time domain aspect of these transitions that will tell us that something is a changing look AGN versus a normal AGN. But what we do see is that the changing look AGN here, the purple line, do tend to have these larger photometric changes, these larger magnitude photometric changes than your sort of typical damped random walk AGN light curves. And so maybe this magnitude of the transition is the thing that will help us pick out changing look AGN. And in fact, you can see here, again, it's not that they occur on some large magnitude and in some space of transition duration. It's that they're really on this sort of tail end of the distribution of normal AGN variability in terms of the magnitude of the transition. So here are our 2 visually classified, strong candidates versus our 4 maybe slightly weaker candidates and all of these simulated damped random walk light curves. And we see that the changing look AGN, the strong candidates for that transition really do occur on sort of the tail end of this distribution. So this is the kind of thing that we are looking for. And that's a nice, first check. But of course, we want to use other information like the color of this transition. So for example, from that simulated photometry, we know that changing look AGN transitions should be very blue. These objects should be bluer when they're brighter. And for that, we're going to have to compare to some real objects to understand how changing look AGN compare to other types of AGN. So this is where we get into some preliminary results. All right, so what I'm comparing to here is a sample of AGN from the Verone SETI and Verone 2010 catalog. Right now, I am still in the midst of matching this comparison sample, so these are very preliminary results. but we are matching to type 1 Seyferts, so those broadline Seyferts, type 2 Seyferts, narrowline Seyferts, and then also to narrowline Seyfert 1s, which are Seyferts with broader lines than Seyfert 2s, but narrower lines than Seyfert 1s. And so what we can see here is that changing look AGN occupy this sort of corner in the G-band magnitude transition versus G-R color transition space that very few other objects want to be in. So there's a couple of type 1 Seyferts that are willing to be up in this corner, sort of above that, like 0.4 magnitude transition in the G-band, 0.2 magnitude change in color, where our strong candidates like to live. There's a couple of Seyfert 1s there. There's a lot of changing look AGN there. And there's no Seyfert 2s there, no narrowline Seyfert 1. So this is probably a good corner to keep looking for those transitions. And again, we do see that there's not really a distinct space in the amount of time for the transition. And again, this is just because that piecewise linear fit is picking out variability on all time scales. So it's really this change in the G-band magnitude and the color that we want to focus on. So we start by getting just some initial rates. We find this kind of transition in 5% of the changing look AGN light curves that we found in ZTF. So that's not all of them, but again, there's a lot of time before ZTF turned on that we may have missed this transition. And we find it in about 1% of the Seyfert 1s. So those might be objects which are occurring or which are undergoing a changing look transition. Those also might just be more variable type 1 Seyferts. And we do not see this transition, this magnitude of transition in any Seyfert 2 or any narrowline Seyfert 1 objects. So this is sort of a promising road to go down when it comes to the changing look AGN. Here we recover J1011, so this object from that Laura Duffy paper, in this transition criterion. So you can see that back in the day, it was on, then it turned off. And then since ZTF has started, it was dim, it brightened, and we know from this Laura Duffy follow-up that it did in fact turn back on. So we are able to recover with this criterion a real changing look event, and that's promising. Here's another object which underwent a changing look event. So in the past, it had a broad line spectrum. We don't have photometry covering this entire period, but once the photometry turns on, we do see a dimming. And after that dimming, we have a spectrum with only narrow lines, no broad line emission. So again, we can't definitively say that this was the changing look AGN transition, but this is a pretty strong candidate. You can see that after this dimming, the light curve is fairly flat. And so it does appear that this object really did undergo this significant dimming, which led possibly to that turn-off event. Now, this is an interesting object. It's a changing look quasar, not a changing look AGN, so it's a little bit brighter. And you can see it's undergoing this really large scale variability. This is after both the on or bright spectrum and off or dim spectrum were taken. And so it's possible that this object has been undergoing repeated changing look transitions and is just on the sort of higher end of the AGN variability distribution. And so these are some objects that were actual changing look AGN, but what about those type 1 Seyferts that also underwent this magnitude of transition? So this is an object which was last observed in SDSS data release 14. And so long ago, it was a type 1 Seyfert. And in around 2020, it dimmed. And so it's possible that this is still a type 1 Seyfert and that this was just part of the normal AGN variability for this object, but it's also possible that this has undergone some sort of changing look transition since the last time it was observed. Similarly, this is a quasar 3C18. So it was last observed in MUSE in 2019 with broadline emission. Since then, it has dimmed significantly, although unlike the last object, this is a really quite variable AGN. And so it's possible that this is just normal Seyfert variability, or I'm sorry, I should say quasar variability that's being picked out by our algorithm. So possibly this is some sort of contaminant. It is also possible that it's undergone a changing look transition, although it does appear to be rebrightening in the past year or so. Here's another type 1 Seyfert, which has dimmed since it was last observed. Again, it's possible that this was a changing look transition, and so follow-up spectra would be needed. But this is also just a fairly variable Seyfert 1, and so it's possible that this is just normal Seyfert variability that is contaminating our sample. And then finally, we have a Seyfert-1, which is actually brightened since it was last observed. And so it's possible, again, that this is normal AGN variability. It's possible that this is some sort of changing look transition. And it's even possible that we have caught a changing look AGN repeating in this sample. And so follow-up spectroscopy would be needed to confirm this candidate. I will very, very briefly touch on the timescale for these transitions. So the median timescale for these transitions is a little under 400 days, with a range from about 100 days to about 1,300 days. And this is most consistent with either the orbital timescale, so the timescale for something to come all the way around the disk, or for the thermal timescale, so for local changes in the temperature to dissipate. And actually, a paper by Colin Burke, a former grad student here, finds this relation if you make some assumptions about the accretion rate of the AGN, that the orbital and thermal timescales should go roughly as the black hole mass to the half. And interestingly, if you look at the, what is that, 6 objects for which we have a black hole mass in this sample, we do indeed recover a relationship between the black hole mass and the transition time that goes as the black hole mass to the half, roughly. This is not really a great fit. It's pretty low certainty. We don't have a lot of data points, but this is the kind of science that you can unlock if we're able to get a large enough sample of these kinds of transitions, like the kind that will be enabled by LSST. So to conclude and to sort of hint at some future work, we find that a good criterion for changing look AGN photometric transitions occurs when there is a 0.4 magnitude change in the G-band magnitude and 0.2 magnitude in G-R color. We found that we were able to find transition timescales ranging from 100 days to 1,300 days, with possibly some kind of relation to the black hole mass. We see this transition in about 5% of the changing look AGN for which we have light curves, and we did find it in about 1% of Seyfert-1s. And so, as I say at the bottom, more rigorous rate calculations, including some weighting by how long of a light curve we actually have, that's in the works. We find 3 candidate objects which may have a repeating changing look AGN transition, and we confirm 1 object which had a repeating changing look AGN transition. We also find 4 potential new changing look AGN in our Seyfert-1 sample, and so further follow-up would be needed to confirm those candidates. So thank you all very much for listening. Thank you to CAPS for the funding, and I am happy to take any questions.
Let's see. So in terms of dimming versus brightening, do you expect that number to be the same, or what does that tell you about what's going on?
Yeah, so right now, that is very, very biased by how we have selected our changing look AGN samples. So the changing look AGN I have here are just a compilation of everything that I could find in the literature that had coverage in ZTF and had over some number of points in the light curve. But most changing look AGN samples are selected in a way that either biases us towards finding the brightening or the dimming, depending on whether you are looking for, say, an object that used to be a quasar in SDSS and is now a galaxy, or if you're looking more for things that have experienced some kind of flare in the G-band magnitude or even in the IR. So I think in theory, depending on which of those original theories is correct, seeing a difference in the rate of turn on versus turn off would be really informative. For example, if almost all of them were turning on, that might tell you that they're more likely to be caused by something like a TDE. But we just don't have an unbiased enough sample of changing look AGN right now to do something like that. So something like this, but as a blind survey in LSST would be, I think, more informative for that kind of question.
Have you looked at other wavelengths? And I know you have a small sample, but is there something that you'd be expecting to see for these?
Yeah, so I haven't, but there is some work by Yang et al. I believe this is her 2019 paper, 2018 maybe, looking in the infrared. And so you see with these, they tend to get bluer when they're brighter and in the optical, and redder when they get brighter in the infrared. There's also been some look at whether or not there's a correlation between changing look AGN transitions and transitions in the radio properties of AGN. And it does not appear that there's a correlation there. There's also been some work in the X-ray, but in the X-ray, you start to get into objects where it's more that you have some sort of cloud obscuring the corona.
So you also mentioned a lot about like AGN variability. So how do you like differentiate AGN variability and changing look AGN? Like, is there like a condition that you separate the two situation?
I don't think there's a 100% separation. I think it's probably two distributions with some overlap. I even think really looking at this simulation with the damped random walk is kind of the best way of seeing it. So if you model AGN variability as a damped random walk, you see that the changing look AGN have pretty significant overlap with that damped random walk variability. Admittedly, some of that is probably just us picking out normal AGN variability. But yeah, even with that, the changing look AGN transition might just be a more extreme version of normal AGN variability. It's superimposed with the normal AGN variability, so it's hard to sort of separate the two. I do think that this sort of magnitude of the change is going to be the place where, at the very least, you get the best separation between the two distributions. I don't know that there will ever be 100% separation.
Follow-up question. Sorry. So in terms of the theoretical perspective, what caused the AGN variability, and do you think it's the same? Like, does the same mechanism cause changing look AGN?
Yeah, so my understanding, and admittedly, this is sort of the level of literature review I'm doing right now as I'm kind of preparing to write up the results, is that normal AGN variability is caused by some sort of disk instability. And so it's possible that changing look AGN are just like a more extreme version of whatever disk instability is occurring there. But it's also possible that changing look AGN are being caused by something else. So it sounds like from the changing look AGN perspective, we really don't know whether this is just extreme AGN variability or whether it's something else. The accretion disk instability models tend to assume that it's like a more extreme version of regular AGN variability.
This is very interesting. I have a couple of questions. So the first one, have you looked at, is there any correlation with the morphology and changing look AGNs? For instance, are all of your changing looks AGN in spiral galaxies and none of them in ellipticals?
Yeah, I really should have a bonus slide on this. My undergrad is doing this right now. So my undergrad, SNe Agrawal, will have a research note out by the end of the month looking at admittedly the galaxy zoo morphology classifications, which I do think are a little bit limited just by the quality of the imaging. We don't see any statistically significant differences in changing look AGN host galaxy morphology and just regular AGN host galaxy morphology. There was one study, Charlton 2019, they looked at Gemini imaging of 4 objects and found that 3 of them looked like post-mergers. I should say 4 changing look AGN hosts. 3 of them looked post-merger. They didn't have like a super solid comparison sample for that. That was more just, that was what they saw. But we don't have high quality imaging of enough of these objects to really get down to like merger signatures. In terms of spiral, whether or not they're barred, stuff like that. Yeah, that was what my undergrad was looking at. We didn't see anything super obvious, but I do think it would be worth doing, especially once LSST has been going for a little while and we have this like deeper high quality imaging of some of these objects. The host galaxy morphology study will be interesting to revisit.
And I had a follow-up because probably these are actually fairly low redshift, so you could actually see the morphology, right? The other thing was all of these are probably, have strong X-ray emission.
Mm-hmm.
And
well, sort of. They're actually kind of on the lower luminosity X-ray end.
Yeah, but they are visible in Chandra or whatever survey, even like on Broset. Has anybody been monitoring when they become dimmer, whether or not somehow they disappear on the X-ray? Is that at all possible?
Yeah, so there's actually a really cool object. So most of them, there is some work monitoring the hardness change through the transition for some of the nearby objects. And I'm going to get that backwards, but that exists. If you ask me after this, I can pull up the reference. But this is a really interesting object. So this is 1ES 1927. And the X-ray corona disappeared through this transition. So this was a weird one. There's a few models to try to explain it. This is also one of only 2 objects that has high cadence spectroscopic follow-up through the transition. It also looks sort of like a TDE. So this one might not be representative of the others. But yeah, this one, the corona appeared to disappear throughout the transition and then reappeared. And so there's been a lot of work on why that might have happened.
And I have a very last short one would be, do you see them turning on and off more than once? I mean,
Yes,
we see, I think that there's maybe like a bias for detecting them when they become brighter. That means, when they go to broader line. But do you see actually them going back and forth, at least in some of your cases?
Yes, there are some. And a lot of the ones that we have seen repeat are the nearby ones that have had longer term monitoring. And those often tend to cycle on timescales of about a decade. So I suspect that if we have some sort of long-term spectroscopic monitoring of some of these objects, we'll see more of them repeat as well.
Great talk. Thank you. My question is about the light curves themselves. So like we can see this transition occur between the on and off or off and on. And that you're saying that the magnitude of that change is roughly similar for these objects, right?
Yeah. Well, to be fair, by construction, I am picking out the highest magnitude ones. So maybe some of them are actually different.
Okay. So then after the transition occurs, there's sort of like slope to some of these curve, like to the light curve itself. And it's continuing to change in magnitude, albeit like very slowly. I'm interested to knowing if there's like an expectation on how the slope of post-transition might tell us about the physics underlying like what's causing the transition itself.
I think that's a really interesting question. I think my modeling would not be a great way of addressing it, because I do think that some of that is going to be biased by things like, did you happen to catch the AGN at a slightly brighter or dimmer moment in its intrinsic variability towards the end of that light curve? So I think you would need a better way of sort of subtracting off the normal AGN variability, which is really challenging and not something that my model can do. Yeah, I don't think there's any theoretical expectations for what should be happening there, but I think it's an interesting question.